Here's an equation that looks like a mess at first glance. The absolute value of x cubed minus 6x squared plus 11 times the absolute value of x minus 6 equals 0. It's cubic, it has absolute values, and it mixes absolute x with x squared. Most people see this and think, this is going to be really complicated. You might be tempted to throw graphing calculators, numerical methods, or brute force guessing at it. But here's the interesting part. There's a really clean way to crack this, and it uses the same substitution idea we use for higher degree equations. Let's look at our equation more carefully. Absolute x cubed minus 6x squared plus 11 absolute x minus 6 equals 0. At first, it looks mismatched. We have absolute x cubed, but we also have x squared. How do we combine those into one clean pattern? Here's the key insight. For any real number x, x squared equals absolute x squared. Whether x is positive or negative, squaring it makes it positive. So we can safely replace x squared by absolute x squared without changing the value of the expression. Let's rewrite the equation using that idea. It becomes absolute x cubed minus 6 times absolute x squared plus 11 absolute x minus 6 equals 0. Now every term is a power of absolute x. That's exactly what we want. This pattern is begging for a substitution. Let's define a new variable, u equals absolute x. This is called substitution. It turns a strange-looking equation with absolute values into a normal algebraic equation in one variable. Just remember, because u equals absolute x, we always have u greater than or equal to 0. Now, replace every absolute x with u. Our equation becomes u cubed minus 6u squared plus 11u minus 6 equals 0. Suddenly, the absolute value has disappeared. We're just solving a cubic. U cubed minus 6u squared plus 11u minus 6 equals 0. Now, let's solve this cubic for u. Instead of using a complicated cubic formula, we'll look for simple integer roots. We try small values. U equals 1, 2, and 3. For u equals 1, 1 cubed minus 6 times 1 squared plus 11 times 1 minus 6 equals 1 minus 6 plus 11 minus 6, which is 0. So u equals 1 is a root. For u equals 2, 8 minus 24 plus 22 minus 6 also equals 0. So u equals 2 is another root. For u equals 3, 27 minus 54 plus 33 minus 6 again equals 0. So u equals 3 is also a root. That means our cubic factors nicely as u cubed minus 6, u squared plus 11, u minus 6 equals open parenthesis, u minus 1, close parenthesis, open parenthesis, u minus 2, close parenthesis, open parenthesis, u minus 3, close parenthesis equals 0. So the solutions for u are u equals 1, u equals 2, and u equals 3. But remember, u was just a shortcut. We really want x, and we defined u to be absolute x. So we now have three equations. Absolute x equals 1, absolute x equals 2, and absolute x equals 3. Let's solve each one. From absolute x equals 1, we get x equals 1 or x equals negative 1. From absolute x equals 2, we get x equals 2 or x equals negative 2. From absolute x equals 3, we get x equals 3 or x equals negative 3. So our six solutions are x equals negative 3, negative 2, negative 1, 1, 2, and 3. Consider the graph of y equals absolute x cubed minus 6x squared plus 11 absolute x minus 6. We're interested in where this graph crosses the x-axis because those are the values of x where y equals 0. That is, where our original equation is satisfied. Absolute x creates a mirror symmetry across the y-axis, so the graph is symmetric. If x is a solution, then negative x will also be a solution. That's exactly what we see with the pairs plus or minus 1, plus or minus 2, and plus or minus 3. If you plot this function, you'll see the curve dip down, cross the x-axis at negative 3, Come up and cross again at -2 and -1, mirror that behavior on the right, and then cross again at 1, 2, and 3. So the graph perfectly confirms our algebra. 6 intersection points at -3, -2, -1, 1, 2, 3, and 3. If you enjoy seeing complicated equations collapse into clean patterns like this, let me know in the comments.